these modern type systems have been found in linear logic, which was a logic that was specifically designed to talk about resources. But there is another big player in terms of logic, separation logic, which is also all about reasoning about resources. And while type systems have been historically inspired and even formally linked to linear logic, there has been only work on program logic based on separation logic and not so much on types based on separation logic. And so the umbrella project for this paper was, what if we base types on separation logic instead of linear logic? What kind of design space do we unlock? And this is not a moot question because the two logics are formally incomparable. And the root of the incomparability comes from giving a different interpretation to the word resource. In linear logic, a resource is something you have a certain amount of. And in separation logic, a resource is something you can tell apart from the rest. And this difference is the root of their incomparability. And so exploring the design space generated by separation logic is an interesting question. Specifically for this project, we've looked at session types as resources. Session types are a family of types that are designed to enforce adherence to communication protocols in message passing concurrent systems. They have been also historically inspired by linear logic, and in a landmark result in 2010, a formal link between linear logic and session types was made, and later then refined by Wadler in 2012. There isn't such a story for separation logic, and this is what this paper is about. What kind of session types and description of protocols can we derive from separation logic? So our contribution for this paper is PyBI, which is a session type calculus, which we extracted from the logic of bunched implications, which is the core of separation logic. For this calculus, we provide a Curry-Howard correspondence with the logic, and we prove that well-typed programs adhere to the protocols and are deadlock-free and are weakly normalizing. And we study the foundations of this theory by providing a denotational semantics to study observational equivalence of the processes, and we study the expressivity of the calculus by providing an encoding of a version of the lambda calculus into the calculus. Now, what does it mean to generate a type system and a programming language from a logic? The idea of Curry-Howard correspondences is that you can draw a parallel between proposition in the logic and types in a programming language, proofs in the logics, and programs in the programming language, such that the proof theoretic properties of the logic translate to behavioral properties of your programming language. And this has generated a lot of nice results. The most classical of which are the sequential interpretations of various logics in various variants of the lambda calculus. What we are interested in is concurrent interpretations for the logics. I mentioned the interpretation for linear logic into a session type pi calculus, and what we do here is a similar story, but for bunched implications. So the goal is to extract from the logic of bunched implications type disciplines for our concurrent calculus for message passing programs. So we are looking at a calculus that at a minimum needs to be able to create a new channel, like in the first line here, or send some message Y over the channel X and then continue, or receive a message Y over channel X and then continue. Then we can put processes together in parallel. And then for technical reasons, we also have a forwarder process that can just copy whatever is happening on a channel Y on the channel X. In our calculus, we also have extra primitives some of which I'll leave for later, and some of which I am going to just omit for brevity, like branching and closing channels. So we have this process calculus here with basic primitives, and a lot can go wrong if you just run it, right? Deadlocks, and all sorts of problems. And what we want is to extract from the logic a type system that ensures some well-behavedness of the processes. So what is this logic we are starting from? BI propositions can be divided into groups. There are multiplicatives and additives. Each of these groups has a notion of conjunction, implication, and a constant for truth. Now, for the moment, I want you to focus on the multiplicatives. Here, I'm just showing a sample of the rules for conjunction, and they work as you may expect. For example, here, to prove that A star B is true, we need to prove that A is true and that B is true. The big twist, however, is that we are forbidden from using the so-called structural rules, which are weakening and contraction. Weakening is the rule that allows you to discard an hypothesis if you find out that you don't need it for the proof. And contraction is the one that allows you to duplicate an hypothesis if you may need it more than once in the proof. Now, the fact that we are forbidding these rules justifies why I wrote the rule this way. And when I need to prove this conjunction, I actually need to partition the hypothesis, delta 1 and delta 2, into different disjoint sets of hypotheses for the two sub-proofs. If I were able to use weakening and contraction, this would not be a restriction. But now that I cannot duplicate or discard hypotheses, this becomes a real restriction. Now, we'll get back later to what this means in terms of the typing, but before we get to the typing, we need to understand how we are going to interpret propositions in terms of protocol descriptions, right? So I'm going to propose this analogy here. We are going to say, okay, the conjunction of A and B is going to represent the specification of a protocol that expects the send of some A, and then will continue as the protocol B. And the arrow type A implies B will be dually representing a receive of some A and then a continuation as B. When we have a judgment like this, we have a number of hypotheses and a conclusion. The hypothesis will represent protocols we can use, and the conclusion is the protocol we have to provide. And since protocols don't just happen in the void, they happen at some channel, we will decorate every proposition with a channel name, the channel at which the protocol is happening. So the only thing missing now is the program to get a typing judgment, right? We converted a judgment from logic to a typing judgment, and the program is going to be the concurrent program that is implementing the protocol B at channel Z, while using the channels that are provided as hypotheses. And now we can understand a little bit this restriction on contraction and weakening, what it means behaviorally. No contraction will correspond to the fact that no aliasing can happen on the channels that we can use, which means that there are no races on the same channel. The absence of weakening, instead, is ensuring that all these channels will be used to completion, which means that no one providing those protocols will be left waiting. So let's see how rules can give rise to typing. Here I'm showing you the rule to destruct a conjunction in an hypothesis, right? We have X, we can use X, this is what the judgment says, we can use X, and on X, the protocol is ready to send an A and then continue as B. Then to use that, we can receive the message on the channel X, and we are guaranteed that that message will have type A, and then that X will mutate its type to be now the continuation B. Now we can look at the flip side of this rule, which is the case when we want to prove that we provide a conjunction protocol. Right? And I'm giving you a fictional rule just to give you the basic intuition, and then I'm going to show you the general rule. So here I'm imagining that we have some basic type for integers, and the type here that I need to provide on X is asking me to send an integer and then continue as B. So the way you would do it is simply by, well, if you have an integer Y, then you would send it over the channel X and then continue as Q, where Q provides the continuation on X. Now, this can work, but what if we have the general case where A is a full other protocol? How do I send a protocol over a channel? Well, protocols happen on channels. So what we're going to do is create a new channel, send that channel over X, and spawn a process P that will provide the protocol A over Y. And then spawn also the continuation that provides X with the protocol B. So we know now how to consume a protocol that sends A and then proceeds at B. We know how to produce one. And so the cut rule is what makes a producer and a consumer meet in the middle. And it does so by saying, okay, we have a producer that produces some protocol A over X, and we have Q that can use that to produce some other protocol C on Z. Then we can create a new channel X and connect the producer and consumer in parallel so that they can communicate. So these are the basic rules for the multiplicative fragment. And actually, the multiplicative fragment is common between advanced implications and linear logic. And so these rules work like in the case for linear logic-inspired calculi. And we also get well-behavedness of protocols, deadlock-freedom, and weak normalization from the well-typeness. But we need more expressiveness, right? This is a very small fragment. And in fact, BI adds the expressiveness by means of the additives. So let's focus on the additives for a second. How do they work? Well, we have conjunction, implication, and truth. And the rules, funnily enough, look exactly the same, but with a twist that for them, now we have weakening and contraction that is admitted. It's available as a principle, right? And here I'm marking this judgment about the additives with a semicolon instead of a comma to emphasize that these are the judgments for which these principles are available. So if we just look at this fragment, can we do the same game of constructing a typing out of it? Well, the answer is yes, but so we want to use the same, we are playing the same game, so the conjunction is still going to be a send, and the implication is still going to be a receive. And the two typing rules are going to be exactly the same, but with the additive constructs. So for now, it's just a switch. The complication is that we also need to support weakening and contraction. Right? And the question is, what is the process interpretation of these two rules? And this is one of the biggest innovations of this work. So let's see what can go wrong with contraction. What is the challenge in providing a process interpretation for contraction? The idea here is that the process Q can use, so we are looking at an example application of contraction. We have an hypothesis A and B, which we are duplicating in the context, right? And in the premise here, Q has access to two different channels with the same protocol. In the conclusion, we need to derive some process that can make use of only one, right? But if we're not smart about it, right? Q can use the resource twice, right, in the same process. And here we only have one process providing the protocol, and this can cause deadlocks if we just let x1 and x2 be aliases of x, right? So our solution is to add a primitive to the calculus, which induces duplication of the providers. So it's a new prefix, it's a spawn, we call it the spawn action, which is at runtime requesting duplication of the provider at a channel. The reduction semantic sketched here says that to run a spawn prefix, x goes to x1, x2, the effect of running that would be to create the new channels x1 and x2 and duplicate the producer at x that is present in the context. At this point, the fact that Q is using both resources is not a problem anymore because we have two independent processes providing the same protocol on both. And of course, in the general case, we may have that this producer itself is depending on further providers on, say, a name Y, right, the channel Y, to provide its protocol on X. And so the full semantics of the spawn is propagating a spawn for the dependencies of the producer so that the dependencies get also duplicated downstream. So we introduced this new action, and it's useful also for the weakening case. In the weakening, we have a similar problem. Here is an example of a weakening, right? We have a protocol sending A here, but Q doesn't really need it and will not use it. And so we would be leaving the provider of X hanging if we just were doing this naively. And what we do is instead insert a killing spawn action that has the effect of killing the provider of X from the context. And of course, it would also work recursively if that provider had dependencies. So we end up with an interpretation like this, and we prove that this fragment, this calculus is well-behaved, deadlock-free, and we get it from the additives. What about the full calculus, right? So we have both multiplicatives and additives in the full logic. Now, things get complicated because now we can both put together hypotheses in a multiplicative way or in an additive way. And so your context for the typing become trees, right? Where we have commas or semicolon as the internal nodes and then the hypothesis at the leaves. And so the rules need to fetch hypotheses inside the tree. And so there needs to be some special mechanism for that. And it's this matching over a tree. For example, here I'm able to apply the rule for deconstructing the conjunction on this leaf because I can look at a subtree here and just apply the rule and substitute that for the little subtree with the conjunction replaced by a semicolon. Similarly, weakening and contraction work by matching the thing that you want to duplicate or drop inside a subtree of the context. For example, because I have a semicolon here, I can apply contraction and forget about B and replace the subtree like this. So now, this is very technical. What is the meaning of the types we get from this overlaying of the additives and the multiplicative? I want to convey the basic idea through a simple example. So what we find is that PyBI has types that can keep track of provenance of data. So let's have a simple example of a memory cell implemented as a protocol, right? So to represent that as a protocol, we have a type which is the composition of a put and a get accessor for the memory cell. The put is simply receiving some data, and it will store it in the cell. And the get will send you the data currently stored at the cell and continue as the cell unchanged. Now assume I'm writing a program, P, which has access to two cells. And these two cells are separated using the additive composition, which is semicolon, right? Now, I can do some interaction with the cell 1 to get the data that it's currently storing. And I can also interact with cell 2 to get the accessor so that I can write something to this cell. And furthermore, if I want to do that, I can send D1, the data I obtained from cell 1, to the put of cell 2 to store that piece of data into the second cell. This is allowed because this arrow type is of the additive kind, and the conjunction I have here is of the additive type as well. But because I have more expressiveness than just the additives, I can do more here. I can be more strict about how the cells are composed. I can say these two cells are separate. They should not mingle. And this would imply that this flow of information from D1 to D2 is now forbidden because I cannot really match on this semicolon anymore. And this is an additive application, and I have a separation here. And just making this flow happen would violate this notion of separation. Now, this is just intuition, but we made this precise by developing the denotational semantics that can give a precise meaning to what we mean by provenance tracking. And this is also giving some meaning for this particular interpretation of BI to the motto, a resource is something you can tell apart from the rest. So all in all, we have introduced PyBI, carry out the correspondence with bunch implications. We studied the denotational semantics and the expressiveness of the calculus. And we just started exploring the design space, and we are very excited about it. Thank you.
So we have lots of time for questions. Yes, going all the way to the end.
I can.
Is that better?
Yeah.
Great. Yeah, well, thanks for a very interesting talk. You mentioned that this calculus is more expressive than the prior ones based on linear logic. Can you give more of a precise characterization of what that means?
So I said it's more expressive than the multiplicative fragment. So the idea is that both linear logic and Bunsen implications have these multiplicatives as the common core, and they augment it with more expressiveness in incompatible ways. And so the PyDeal work and the work that extracts PyCalculus from linear logic follow the way to extend the multiplicative fragment of linear logic, which gives rise to some primitives, right? For example, the bang operator, right, of linear logic becomes the bang operator of the PyCalculus, which is a very specific form of forming a server, which is interesting in its own right. Here we obtain, it's basically the way that BI adds expressiveness to the multiplicative fragment is, you can see it as an alternative to exponentials for having nonlinear resources. And what we find is that you can use these facilities to mimic some sort of server client patterns as well, but they are of a different kind than the one that you find in linear logic.
So in particular, am I right that you can have data races?
You cannot.
Oh, you cannot have data races? Okay.
The behavioral properties are the same. In terms of deadlock freedom, and deadlock freedom is ensured in the same way by saying that you never race on a channel. And the reason is that if you look at how the spawn works, here, I'm duplicating the process. When I need to use the same channel multiple times, what we want to have is two independent copies of that channel so that we can independently interact with them without creating any deadlock or problem, right?
So that looks very similar to what an exponential does in linear logic, but
it is not, and the reason is that in the exponentials, it is the responsibility of the banked resource to allow for replication, right? It's the server that needs to say, okay, I can do this protocol. I now give you the possibility of spawning multiple copies of this protocol. I decide that I'm able to do that. Here, the server is completely unaware of how it's going to be used. It provides one run of the protocol only. And now it's the client that will decide, oh, you know what? I want to use it twice. And the spawn prefix will have the side effect on the context of duplicating the server for you. So it's very dual to how the exponentials work.
okay, thanks. I have lots more questions, but I'll ask you them.
Any more questions? Right behind you. Yeah.
Hi, thanks for a nice talk. I was wondering, so in CP, you've got the combined name restriction and parallel composition and the combined send and parallel composition. I was kind of surprised to see in separation logic, which does give you that notion of separation, that you still have these combined constructs. Could you see a potential reformulation which would allow you to take these constructs apart?
That's an interesting question. So I was expecting something similar too when I started out. But it turns out that at least this was more interesting. So if you go for something very intuitive but very simple, which is, oh, if I have separation, it means I have in parallel two things that don't talk to each other. It's all of a sudden very boring, right? Like, what would then be the type for sending if you use the conjunction for independence that way? But it could be interesting to, I mean, this is only one correspondence, right?
Okay. All right, let's thank Emmanuel again.